Right. Today we're going to solve some exponential equations and also do a little introduction to logarithms. And what I have pulled up here over to the side is all the lists of the perfect squares, perfect cubes, perfect fours. This list is going to be really helpful today. The first little part of this is just to review maybe how we can rewrite a number as a number with a base that has an exponent. So I just did the first one real quick. 25, I'm just going to rewrite that as a base number, which is the 5, with an exponent, and the exponent being squared. So another way we can write 25 is 5 squared. And I can just get that right off this list. This is 25. It's in the second column, so it's going to be 5 squared. If it's in the third column, like 125 would be 5 to the third, 625 would be 5 to the fourth, the 3125 would be 5 to the fifth. So this little list, if you're not familiar with it, can be really helpful today and for the rest of this unit. So 64, you'll notice 64 in a couple different places on the list. You're going to see it as a perfect square. So 64 is 8 squared. It's also on the list for perfect cubes. So I could also write this as 4 to the third. And I know my list does not continue over farther than this. If we got into the perfect sixth, the next level for your twos, it's like 4, 8, 16, each time we're multiplying by 2. 64 can also be written as 2 to the sixth power. So there's actually 3 different ways I could write 64 that had a base with an exponent. Okay, the other thing I want to review with you really quickly is what we have for negative exponents. So this is 1 over 2. I just want to remind you another way I could write that would be 2 to the negative 1 power. So if you have a fraction, you can turn that into a number base with a negative exponent. This is just 2 to the first. 2 is not on any list over there that you're going to rewrite that in any other way. 9, however, this one is 1/9. So let me just do a step here. This is 1 over 3 squared. And if I want to write that as just a base with an exponent, this is the same thing as 3 to the negative 2 power. Now, we've said all along here, expressions are not simplified if we have negative exponents, and that's still true. However, using just a plain number to an exponent, positive or negative, today is going to help us solve some of these problems. So if you need to use a negative exponent to help you with the problem, that's okay. And then finally here, if you guys come over, I kind of already mentioned this, 125 is in that third column, so it's going to be 5 to the third. So this would be 1 over 5 to the third, or just as a plain number with an exponent, 5 to the negative 3. Fractions are not negative exponents are not negative numbers. Fractions have negative exponents. Okay, so today we're going to work on some exponential equations. And exponential equation is exactly what it says here, an equation where the variables and the exponent. So if you kind of look down the page here, you'll see variables in the exponents of what you've got in front of you. Now, we're going to use some properties of exponents today as we go through. So if you guys remember, let me scooch this up and I'll pull our list back up in case we need it. I have like bases here, okay? So if I multiply like bases, I'm not really going to be able to simplify anything on the left side of that equation. So I'm going to leave that as 3 to the 4x power. Over here, if I multiply like bases, what you do with the exponents is add them together. So what we can do here, since these are both 3, I'm going to take those exponents. I have 6x, and then I have 5x minus 14, and I'm just going to add those together. If you multiply like bases, you would add their exponents. And so then, really all I can do here is do a little combine like terms. I can change the 6x plus 5x into 11x. We can actually combine that. And then what you're looking for here to continue to do this problem, on both sides of this equation, I have 3 to a power. So this is 3 and this is 3. These exponents have to be equal to each other. So to solve this problem, we're just going to do 4x equals 11x minus 14. And just solve this like a normal equation. If it's me, I try to keep my variable positive, but here it's going to be fewer steps if I subtract that 11x from both sides. We're going to end up here with negative 7x equals negative 14. And then I didn't leave myself enough space, but if I divide both sides there by negative 7, x is going to be 2. So the missing exponent up there is going to be 2, and you can plug that back into the original problem if you want to check. Now, the rest of these equations, these all had a base of 3 when I looked at this problem. The rest of these equations, we're going to have to do a little manipulation with kind of what we did in the very first problem at the top to get the bases to be the same. Okay, so my next equation here, let me slide this over. I've got 5 to the 2x minus 4. I have this 25. What I want to do, since I have a base of 5 here, is I want to try to rewrite 25 as 5 to a power, which we can do. So this is 5 squared. So I'm just rewriting. When you do that manipulation, then I have both of these being 5. And so that forces the exponents to be equal to each other. So all we have to do is 2x minus 4 equals 2. Solve that little equation. I'm going to add 4. I'm going to get 2x is equal to 6. We'll divide by 2, and then x will end up being 3. But to do that, I have to first make the two sides have a matching base, and then I can set the exponents equal to each other. All right, let's slide this here up a little bit. And I'm probably gonna, I'm gonna lose my, let me pull those guys back up for you. There we go. Okay, all right, now this one, I'm dealing with 32 and I'm dealing with 8. So come over here, and if you're seeing these numbers, like here I see 32, here I see 8, what we're going to do for this question is rewrite both the 32 and the 8 so that they have a base of 2. So 32 is 2 to the 5th, and this will be a little bit different than each of the questions we've done so far. And if you guys are looking there, 8 is 2 to the 3rd. Okay, now so far we haven't had this, but in this question we are rewriting, and then we have an exponent x minus 1. When I rewrote, I have the exponent here. This is the 32. 2 to the 3rd is the 8. So now we're introducing another property of exponents. What you need to do here, power to a power, you multiply the exponents. So on this side here, that 5 would get multiplied by the exponent, and then it has two terms, so be real careful. We need to use a distributive property there. This one, 2 to the 3rd, I'm going to take the power to a power, so it'd be 3 times 2x plus 3. And then make sure you put that in parentheses, because you have to power to a power when you multiply the exponents. I'm multiplying 3 by all the parts of that expression. Okay, now once I've done that, my two bases match. So just like the questions we've done above, that means the exponents have to be equal to each other. And you could simplify that there, or you could just go ahead and write your equation and then do the distributive property, whatever is easier for you. I'm just going to write that out. This would be 5x minus 5. This would be 6x plus 9. And then we're just solving that equation. So I did a little distributive property. I like to keep my variable positive if I can. So if I was doing that, I'm going to subtract 5x from both sides. 6x minus 5x just leaves us with 1x plus 9 here. Move the 9. And that's going to give you negative 14 as your answer. And again, any of these, if you want to go ahead, plug them back into the original problem and check, they should work and they'd be equivalent on both sides. All right, now I have one more, and this is probably the trickiest question of all. I have three different things going on here. I have a 27, I have a 3, and I have a 9. And so I would like to make each one of those as a base that's the same. So what I would recommend there, these are all related. These can all be written with a base of 3. So 3 is already fine, so I'm just going to leave that alone. 1 over 27, let me just write this above here so you can see what I'm doing. This is 1 over 3 to the third power. And if you're like, what the heck? Here's the 27. If you're looking at your list of perfect cubes, it's 3 to the third power because it's in that third column there. So that's real quick. What we're going to do here, though, I don't want to deal with the fraction, so I'm going to convert that to have a negative exponent. So 1/27 is the same thing as writing 3 to the negative third power. Okay, so then we still have this 2x minus 10. Now, I'm going to leave this term, the 3 to the 4x plus 12. We'll just leave that alone because it already has a base of 3. 9, if you come over to your list of perfect squares, right there, 9's right next to the 3. In the second column, that means it's 3 squared. Okay, and so then, let me slide this over here. What we're going to do is, I'm just going to simplify just a little bit. Power to a power, I would multiply the exponents. So this would be negative 3 times this negative 2x minus 10. And this side is going to be multiplying like bases. If you're multiplying like bases, I'm going to take and add these two exponents together. So this is going to get kind of complicated here. So 4x plus 12 plus, now here I have to do that power to a power because I rewrote 9 as 3 squared. So this would be 2, and then don't forget the parentheses, times 2x plus 5. Okay, so a lot more complicated, but it's just going to be solving an equation. So once we've got this all set up, both sides have a base of 3. So if the bases are the same, that forces the exponents to be equal to each other. So here's my question. I'm doing 3 times negative 2x minus 10. That has to be equal to the 4x plus 12 plus 2 times 2x plus 5. Now, like I said, if you want to do, you can do the distributive property as you go through. These don't have to be all these separate steps, whatever's easier for you. I am going to go ahead and do the distributive property here. Negative times a negative is going to make this positive 6x. Negative times a negative here is going to make this positive 30. All right, and then I'm just going to write the 4x plus 12. Little distributive property here. 2 times 2, 4x. 2 times 5 is 10. And totally up to you how you do this. I'm going to go ahead and combine my like terms here. I have 8x and I have 22 on that right side of the equation. And then I like to keep my variable positive if I can, so I'm going to subtract 6x here. And I'm just going to do this all in one step because I don't have a lot of space at the bottom of the page. And then I'm going to move that 22 in the same step there. So what I'm going to be left with, this cancels and this cancels, I'm going to get 8 is equal to 2x. And after all that work, divide by 2, and my answer there is going to be 4. Okay, now on the back we're just going to do a little introduction to logarithms, and the reason we are doing this, we're working with exponentials on the front. The logarithm, also called just a plain log, kind of as a little abbreviation, the inverse of an exponential. So I've got two formats here for you to look at. This is what we call exponential form, where we've got our variable and our exponent. And this is what we call log form, and these two are related, and you can convert back and forth between the two. The way this works, which we'll get into here with some of these examples down here, the base of the log is going to swing across and become the base of your exponent. So these are related. Exponent in the expression is in the logarithm in the equation, so you guys can see the relationship here. This is kind of a textbook definition. And it's the same base, just kind of like I mentioned. Now, there's two rules here. Your base here and your base here cannot be equal to 1, And that's just simply because then it wouldn't be exponential, because if I put a 1 right there, 1 to any power is 1. So that's not going to happen. And also, it cannot be a negative number. So b greater than 0, this just means b is positive. That's what that means. Greater than 0 means I'm positive. And then this kind of explains here, a positive number b raised to any power x cannot equal a number y less than or equal to 0. You can't get a negative there. So the log of a negative number 0 is undefined. So we'll keep that in mind today as we go through, and we'll get more into that for our next class. All you're going to do here in this example 2, we're just going to convert from exponential form. These are all exponential form. You don't see any logs. We're going to convert to the log form. So I'm just going to kind of show you how to do this. And these can be written in different formats. Some of these are written in where the exponent's on one side of the equation, some of them the exponent's on the other side. So here's what I would have you do. The base of your exponent, you're not solving anything here, we're just converting this to log form. This slides down to the other side of this equation. The base of your exponent becomes the base, little subscript is another way to say that, of your log. So this is going to come over here, keep the 32 where it's at. When you swing that down, that exponent comes down on the level with the rest of the equation. So these two things are equivalent. This is their exponential form, this is your log form. Okay, I'm going to do the same thing on the next question. The base of the exponent is going to swing down across that equal sign and become the base of the log. So log base 3 of 729, keep that where it's at, and then that exponent comes down onto the level with the rest of the equation, and that's going to be equal to 6. Okay, these are kind of written backwards from that first two. So here the exponential is on this side. Now, this is just a thing for me personally, but I like the log to be on the left side. So if I was doing this question, and you don't have to rewrite it, but I'm going to put the log on the left-hand side. So that's just kind of how my brain thinks about it. But the same process, the base of your exponent here is going to be a half, is going to swing across the equal sign and become the base or the little subscript of the log. So log base 1/2 of 1/8. When I swing that across, it kind of like pulls the exponent down to be on the level with the rest of the question. I'm going to do the same thing here. Like I said, I just prefer the exponential, so I can swing that back across there, and I swing it back to the left. So the 12 here is the base. And these are all true statements. Like 2 to the 5th power is 32. 3 to the 6th power is 729. These are all true statements. Anything to the 0 power is 1. For the example here, this is 12. Swing this back across. The log base 12 of 1. And then as you swing that down to become that subscript, that exponent gets brought down on the level with the rest of the question. So there's your log form. Log base 12 of 1 equals 0. And then I have one more here that, again, this is just my thing. I'm just going to rewrite this real quick. And this is true. 1 over 100, 100 is 10 squared, that negative exponent, because that would be 10 squared in the bottom of that fraction. To convert this, I'm just going to take my base of my exponent becomes the base of my log, swing that over there. This will be the log base 10 of 1 over 100. As I swing that across the equal sign, that brings that exponent down, and that's going to be equal to -2. And then what we're going to do in the next example is reverse that. So the next example, each of these equations is log form. These are all true statements. We're going to convert these to exponential form. So to do that, we're just going to reverse the process here. We're going to get rid of the log by swinging this base. And when I swing this base, it's going to push that exponent, this 4, it's going to push this up in the air. 256 is 4 to the 4th. So what I'm doing, let me highlight this because they're the same number. This 4 is becoming this 4. It's going to push that exponent up in the air. Let me do one more here. Okay, so to get rid of the log, you swing the base to the other side and it pushes that number up into an exponent. So this one would be 27 is equal to 1/3. I'll just put that in parentheses so it's a little easier to see there, to the negative third. So when I swing this, the base of my log becomes the base of my exponent in the exponential form. And we'll just do one more. So I'm going to swing this. And this is actually the question we did just right above there, just to relate these. So to get rid of the log, you swing the base to the other side. It pushes that up into being an exponent. So leave the 1/100 where it's at. This will be 10. I'm going to push this up to the negative 2 power. So the base of my log here becomes the base of my exponent. And that's just converting a log form to an exponential. Okay, so a common logarithm, just as a definition, so you can see this, common logarithm is a log with a base of 10. And any of these can be done on the calculator, the log base 10. If it has a different base, like if you guys look down here, you've got a 3, you've got a 9, you've got a 5. You can't do those on the calculator. Calculators are programmed to be in base 10. So the other thing you might see, just as a heads up, if you literally just see like the word log and you don't see a base, we're going to have a couple examples like this in a second. But like, let's just say I took the log of 100 and that was my problem. They don't write the base in for the common logarithm majority of the time. So that is equivalent to the log base 10 of 100. And we're actually going to evaluate these in the bottom step, or the bottom example here. So easiest thing I can tell you to do, if you are evaluating something, you should get a value as your answer. So I need a number answer for each of these questions. Each of these are logs that cannot be done on the calculator, with the exception of this problem here, because it's base 10. It just says log, so it's base 10. But we are going to ask you guys to do these without a calculator. You have to be able to do this, no calculator involved. And so this is, again, if you're not familiar with these numbers, where these lovely numbers are going to be very helpful to you. Okay, the easiest way I can tell you to evaluate a logarithm, let me slide this to the side so you guys can see those numbers pretty well. What I always do is convert it to exponential form. That's what we were just practicing. So each one of these, they don't have any equal sign or anything like that, but I'm going to create an equal sign by just writing this equal to x, because we're going to try to evaluate this. Okay, now what you want to do, I'm going to convert this from log form to exponential. So the base of my log, I'm going to swing it across the equal sign, push it up and push that x up in the air. This will be 81 equals 3 to the x. And again, the base of my log becomes the base of my exponent. Okay, now come over here and I want to see if I can find 81. And I've got a couple options. 81 is 9 squared, but 81 is also right here 3 to the 4th. So because this is a 3, what you want to do, let's use the 3. I'm going to rewrite 81 as 3 to the 4th power. So just straight up 3 to the 4th power. And if that's the case, just kind of like the equations we were doing on the front, if the bases are equal, then the exponents are equal. So this would literally be 4 is equal to x. And really, I just need my answer to be the 4. That's what I'm looking for there. You have to be able to do these without a calculator. Okay, so let's try this again. Just if you have to evaluate a log, just set it equal to x. We're going to convert it to exponential form. I'm going to swing this 9 across the equal sign to get rid of the log. So the log goes away, 9 pushes that x up in the air to be in an exponent. Okay, I cannot rewrite 27 as 9 to some power, but I can write both of these as 3 to a power. So I'm going to do two things here. I'm going to rewrite 27, 3 to the 3rd, and I'm going to rewrite 9 as 3 squared. Okay. Now, what I've got going on here, I've got 3 to the 3rd and power to a power. This would be 3 to the 2x. Okay, if my bases are the same, that forces my exponents to be equal. Here is a little bit different than the last question because it was just a 4 and an x, so this is a little different. What you would do here, 3 is equal to 2x, divide by 2. So here, 3 over 2 is going to be my answer to that. All right, let's try another one here. Just set these equal to x, change them to exponential form. Swing base of the log, pushes that up in the air, becomes the base of your exponent. This is going to be 5 to the x. Try to rewrite both sides with the same base. We've done this a couple times today. So 25 is 5 squared. If the bases are the same, that forces the exponents to be equal. So here, this would be 2 equals x, or just go ahead and write 2 as your answer. I'm going to slide this back. And actually, let me slide this up a little bit so you guys can see. And I'll pull back up those perfect roots. Okay, so again, each one of these I would just set equal to x. Easiest thing I can tell you to do. Swing the 8. 16 is 8 to the x. Okay, now 16 I think of 4 squared, but I also come over here, have it as a 2. You need to rewrite both 16 and 8 because I can't write 8 with a base of 4 like I can 16, so I'm going to write both of these with a base of 2. 16 is 2 to the 4th. 8 is 2 to the 3rd. So this is kind of similar to part B here. This would be 2 to the 4th equals 2 to the 3x. Here, once my bases are equal, my exponents are forced to be equal. So I'm just solving this little tiny 4 equals 3x to get my answer. So 4/3 is going to be the value of the log base 8 of 16. All right, here's what I mentioned just before we started this example. If you don't see a subscript, this is log and it doesn't say anything else. If you don't see a subscript, you go ahead and assume that to be base 10. Now, I personally like to put the 10 in there because I like to visually see myself get rid of the log by swinging the base. So that's how I would do this problem. But if you don't see a subscript, it's assumed to be base 10. So I'm going to swing that 10 over there. This is 10 to the x. Okay, now if you guys come over to your perfect roots over here, 1,000 is in the third column with the 10, so it's going to be 10 to the third power. Now, I'm just going to kind of do a little aside here. This would be 1 over 10 to the third then. What I want to do though is because I have a fraction, I can just convert that to a negative exponent here real quick. So this would be 10 to the negative 3. And then both of these have base 10, so that forces my exponents to be equal. So this would be negative 3 is equal to x. So the log of 1 over 1,000 would be equal to negative 3. And I have one left here. This one's kind of the trickiest. I'm going to swing. I got log base 64 of 1 over 32. Get rid of the log by swinging that 64 over to the other side. That 64 pushes that x up into being an exponent. Okay, kind of come up here, look at the 2's. 32, and I need another column on this, I think. 32 is right here. 64 is going to be the next one over, which you can't see here because I don't have that column, but 32 is 2 to the 5th. 64 is 2 to the 6th. I have to use a base of 2 because 64 can be written as several different bases, but 32, the only base you can convert that to, is going to be a 32. This is going to be 2 to the negative 5th. I will write that to the side in 1 second. 64 is 2 to the 6th. Let me write this here kind of like I did on that last question. This is 1 over 2 to the 5th, which I can then convert to having that negative exponent there. All right, so here's what we have. We have 2 to the negative 5th equals 2 to the 6x. Once our bases are the same, they're both 2 here, that forces our exponents to be equal. So negative 5 has to be equal to 6x. Oops, sorry, let me slide that. So I would divide both sides there by 6. So that last answer is 5/6. And any of these You could plug them back into this step where we converted it to exponential form if you wanted to check. You can't check these on the calculator other than this letter E here because the calculator does not do base 10.